Welcome back, everybody. Today we're going to continue our review of differential equations and their solution methods by going through some modeling basics. We'll go through, I think, about 5 examples of different models and solve some differential equations using some of the techniques that we discussed last time. And then, I think, depending on how long that takes, we may do a little bit of an introduction to Taylor series before next lecture, when we really kind of get stuck in and start to develop some numerical differentiation schemes using Taylor series. But for now, to get started, like I promised at the end of the last lecture, let's actually go through, and before we start solving some differential equations and setting up some mathematical models, let's go through the taxonomy of differential equations, right? So, these terms that I was using in the last lecture that, to be frank, you should be familiar with at this point, but you've likely forgotten what some of them mean, like linearity, homogeneous, non-homogeneous, those types of categorization methods. Let's go ahead and go through and write down what each of those are. So the first thing that we'll discuss is ordinary differential equations. So I think I may have said this one, at least verbally, in the last lecture, but an ordinary differential equation is a differential equation, which I'll abbreviate DE, with only one independent variable. Okay, so if you have multiple independent variables, it's a system of coupled ODEs. So it has only one. There's a second. There's a second condition here beyond it just being with one independent variable. The derivatives are taken with respect to that one independent variable. With respect to this independent variable. If you have multiple dependent variables, so notice I'm saying dependent variables, so multiple quantities that depend on that one independent variable, you end up with a system of coupled ODEs. Okay. And then the other type of equation that we will really get into towards the end of this class, in 6 weeks or so, is partial differential equations. So this is where you have, it's like an ODE, but you have greater than one independent variable. Greater than one independent variable. Okay, in our case, this is often like X, Y, Z, and T. So the 4 spatiotemporal dimensions will be the independent variables that our quantities will depend on, in most cases, when you're solving physics problems. So what do we mean by order of a differential equation? This is the order of the highest derivative in the differential equation. Order of the highest derivative in the differential equation. This also determines the number of conditions necessary to specify a solution. Should probably note that as well. Determines number of conditions needed to specify solution. Okay, so now what about linear versus nonlinear? So linear versus nonlinear. If terms appear as nonlinear functions of the dependent variable, then the differential equation is nonlinear. So if terms appear, terms in the overall differential equation that is, as nonlinear, and what do I mean by nonlinear? Here I mean by things like, sine of x, or x squared, or e to the x. Those are all nonlinear functions of x. Okay, so appear as nonlinear functions of the dependent variable or its derivatives. Then the differential equation is nonlinear, and vice versa. So if you have no nonlinear terms show up, then of course the equation is considered linear. Okay. Then there's the notion of homogeneity. So homogeneous. This is if all terms contain the dependent variable or its derivatives, then the differential equation is homogeneous. Okay. And just a couple more definitions. So you have initial value problems. These are problems where the conditions, or all of the conditions, are specified at the same location of the dependent variable. The same, and I'll put location in sort of quotes here because we could be, most of the time, initial value problems are actually time domain problems. So it'd be like a location in time, which is just at a specific time of the dependent variable. So this is, even if it's a second order problem, say you have two different conditions that are specified both at like time equals 0, for example. But we also have boundary value problems. And this is where at least two conditions are specified at different independent variable locations. This should be independent up here, sorry. At the same location of the independent variable for initial value problems. And then we say at least two conditions specified at different independent variable locations. Okay, so for now that should get you all the way there with differential equation categorization. Okay, so let's, as promised, move on to some modeling examples. And we will start with a classic in physics, which is the pendulum. So say we have a sort of a ceiling here, and then a bob on the end of a string. The bob is going to have a mass m, okay? And we will define this datum, which is straight down from the ceiling, and the bob's angle off of that datum will be theta, and the bob itself will be, or the string will be of length L. And if we were to draw the forces acting on this, we have the tension of the string, of course, which we don't need to draw on the diagram, and then we have the force of gravity pulling down mg. Okay, and what we'd like to do here is to apply Newton's second law. In the azimuthal direction. And why do we do that? Well, it's because the force is balanced in the radial direction. And what do I mean by radial and azimuthal in this case? Well, radial is the direction where we're sort of taking the pivot of the pendulum system to be the center of the circle. So radial is pointing towards the pivot or along the string. And so we can break down this mg force into two components. One that's in the azimuthal direction here, which is going to be mg sine theta, and then one in the radial direction, which is mg cosine theta, but that is always balanced by the tension in the string. So that's an uninteresting direction, let's say. Okay, so if we do that, we just take f sub theta to denote that it's the azimuthal direction is equal to ma in the azimuthal direction, right? And let's go ahead and try to find a mathematical form for a theta in terms of our independent variables. So the distance that the bobbit or mass travels in the azimuthal direction in terms of theta is equal to theta times L. Okay, it's like a chord length on a circle. And so therefore our excuse me. Therefore our velocity in the azimuthal direction is L times d theta dt, and our acceleration in the azimuthal direction is L times the second derivative of theta with respect to t. Okay, and then how can we express the force in the azimuthal direction? Well, that is where we use mg sine theta, but then we want to choose the correct sign. In this case, the way we've drawn the diagram, it's always a negative here, mg sine theta. So it's a restoring force that's bringing us back towards theta equals 0. Okay, so then we plug both of these things in to our governing physical law, which is Newton's second law, and we end up with an ODE of the form m times L times d squared theta dt squared plus mg sine theta is equal to 0. Okay, and we can divide both sides by m, or the entire equation by ml, and also move to sort of the actually I think it is a Newtonian notation, the dot notation, which is commonly used for kinematic systems. So theta dot dot is the second derivative with respect to time. It's always, the dots always tend to denote a derivative with respect to time. And then we're going to define this new constant omega times sine theta is equal to 0, where omega is equal to the square root of g over L. Okay, and we define it that way because as you'll see, the fundamental frequency will end up being that square root of g over L. Okay, so let's kind of practice with our categorization rules here. Here we have it's second order because we have a second order derivative, so it's second order. It is nonlinear because we have that sine of theta in there. And it's also homogeneous because there's not a term that does not contain the dependent variable or its derivatives. And it's an ordinary differential equation in ODE. Okay. And then we're going to specify some initial conditions, which is that theta, or the initial displacement at time equals 0, is equal to 10 degrees. And we'll say that the derivative of theta at time equals 0 is equal to 0. In other words, we're lifting it to 10 degrees displacement and we're dropping it. Okay, and since both of these are specified at t equals 0, that makes this an initial value problem. And then here's a very, very common assumption that we can make because this initial displacement is very small. Which is that theta remains small for all time. Okay, so sine of theta is approximately equal to theta. Okay, and once we discuss Taylor series, this will become even more obvious as a simplifying assumption. But just to make the case really quick, if I plot, sine of x as a function of x, it sort of looks like this, right? And if on the same graph I plot x in red, it looks like this. Okay, so you can see that when x is small, x being small in this sort of area right here, these two things are right on top of each other. Sine of x is approximately equal to x, and that's the general idea there. So those two are about the same. They have the same functional. The functions look roughly the same when you're close to x equals 0. Okay, so then what that does is that allows us to transform our nonlinear equation into the linear equation, which is just theta double dot plus omega squared theta is equal to 0. So we went from nonlinear to linear, and moreover, it's a second order equation with constant coefficients. So the way we're going to solve that is with the method of the characteristic equation, rather. since it's also homogeneous. Okay, and you know, we won't go through the details, but what you're going to end up with is theta is going to be some sort of sine of omega t and cosine of omega t. Okay, it's just going to be a sine and cosine with a frequency omega t. I encourage you to go through and actually do that, but in the interest of time, we'll go ahead and leave that to you, since it's such a simple application of the characteristic equation. Okay, so let's go ahead and move on to our second example, which is another example with one of Newton's law, which is Newton's law of cooling. Which actually, which itself was published anonymously. So everybody's aware of his laws of motion, which were published in the Principia Mathematica. But his law of cooling was published anonymously in 1701, and I actually went and found the start of the original publication. You can see it's in Latin, but it's kind of fascinating. So this is a portrait of Newton, by the way, who was actually my 14th great grand advisor. This is a fun fact, but you can see that this bottom half here is where his publication begins. But I actually find this page most interesting because it contains this discussion of grabbing a drop of water from like a river and looking at it under a microscope, and you can see that he says, "I took a drop thereof, and in it discovered a mighty number of living creatures." And then it talks about the water drying out and the animals dying, and how everything is looking at a river fish, of a jack or pike. All these things is so fascinating. First of all, it's just funny that this is, I think these are probably the proceedings of the Royal Society. So they're just publishing, some guy's just publishing his observations of looking at a drop of water under a microscope. And it's very possible this is Robert Hooke himself who discovered the microscope and was active in that time. So this could be one of his articles. In fact, there's a book you can buy that's I forget what it's called at the moment. It's escaping me, but it's essentially a collection of his drawings that he did. I think it's called Micrographia by Robert Hooke. And they're just these beautiful, really detailed drawings of creatures like a flea that he drew, looking at them, these specimens under his microscope, because he developed this apparatus. He was the one who invented the microscope, and it's super fascinating. I mean, the drawings are beautiful. His observations are beautiful. Though he writes about, the satin armor of the flea, with such great enthusiasm. It's great. It really shows that spirit of science, and it's really fun to look at those types of old publications. I encourage you guys to take a look. Okay, so what we're modeling in this case, though, with Newton's law of cooling is an object. So think of an object of a steel ingot in a large thermal bath. So that's that's the same thing as something like a steel ingot in the middle of a big empty room or a big tank of water. Okay, at temp T infinity. So that's the temperature of the thermal bath. We know that from Newton's law of cooling that the time derivative of the temperature of the ingot is equal to minus K, which is thermal conductivity, times the temperature difference between the ingot and its surroundings. Okay, so one important thing is because of this term here, this is a non-homogeneous equation. So first thing to note. Okay, but it is a separable equation, right? So, you know, the way you would solve it is relatively straightforward. You know, you'd integrate both sides. You'd have like 1 over t minus t infinity dt is equal to the integral of minus k of dt times minus k. And we've done this integral a couple times already in this class, so I'm not going to do it again. But you would end up with exponential cooling or exponential decay of the temperature to the surroundings, or exponential growth of the not exponential growth. It's always slowing down. So it's asymptotically approaching the asymptotically approaching the thermal bath temperature, the ambient temperature. Okay, so that's one example. Another modeling example. A further example is oil coating. Okay, so this is viscous fluid flow. And the right equation to describe this is Navier-Stokes. Okay, and so Navier was born in 1822, I believe, and Stokes born in the 1840s. And I think I have an image of them too. Yeah, so this is Navier and Stokes. The bust is of Navier, and Stokes is this gentleman on the right. Stokes has a lot more had general contributions to vector calculus. Navier-Stokes is kind of an interesting had an interesting history where he was a structural engineering student of Joseph Fourier, who has all sorts of amazing contributions, and we'll actually touch on one of his contributions later in this lecture. But here's the situation that we wanted to describe here. So we have a conveyor belt. So that's what this is, to make it clear. It's conveyor belt. And it's moving upwards, okay, constantly. We'll define our axes like this, x and y. And let's say that we have a large oil bath that is level out here. This is an oil bath. And it has some sort of viscosity and density. Okay? And when you draw this conveyor up out of the oil bath, there's a slick of oil that, due to the friction with the conveyor belts, sort of is wicked upwards, right? Okay, and at the top of in the end, you're going to have some sort of thickness of oil attached to the conveyor belt, a thickness h, lowercase h. We also have gravity acting downward, of course, and then we're going to assume that beyond this dashed line here, from that point upwards, the flow is what's called fully developed. Okay, so what fully developed actually means is that the flow does not change along the flow path. So flow does not change along flow path. In this case, that's in the positive y direction. Okay, and so now we want to, with this setup, we want to solve for the velocity profile of the flow in that fully developed region. Okay, and the general equation for the vertical velocity of the flow is the following. So using just Navier-Stokes. So general equation, and I'm going to put down some vector operators here, which might confuse you, but we can go through them. I'll spend some time explaining what each of them are, but this is going to be, you know, all three components and all of its glory, the Navier-Stokes equation, or Navier-Stokes equations, I should say. So it's the partial derivative with respect to time of the velocity of all three components. Okay, so this, what I'm writing down here is actually a vector equation for the three different flow directions, plus v dot grad. So this is the gradient operator. And I'll put a little vector above it there. V is equal to minus the gradient of the pressure divided by rho plus g. So all three components are encapsulated here, all three components, because it's in vector language, right? V itself has three components. It's U, which are usually in the fluid mechanics context denoted as U, V, and W. That would be the X, Y, and Z component of the flow. Okay, so first off, we're actually, so X and in Z, sort of into the page, we're assuming that there's basically no flow in either direction in the fully developed region, right? So we have no because there's symmetry into the page. We're assuming this is sort of like an infinite conveyor belt coming out of the page. We wouldn't expect there to be any flow in the Z direction, and we know that there's no flow in the X direction because the conveyor belt is just simply moving upwards. So we can simplify down to just looking at the Y components. So that would be the V. Okay, and so we have dV dt minus mu over rho, once again, times the Laplacian of V. So that's that I'll write out what these operators are just in one moment, because I think that when I first taught this, most of the students had not seen these vector operators before. So I'll make it very clear in just a second what those are. So we still have V dot the gradient of V here on the left, because we haven't dealt with those operators yet. And we still have, actually we're going to just lift the Y component of the pressure gradient, because we're only concerned with the Y component. So we have 1 over rho, negative 1 over rho times the partial derivative of the pressure with respect to Y minus G. Okay, because we're in that Y component. So let's sort of scoot over here and look at what nabla is, or nabla, or the gradient operator. The gradient operator itself is a vector of derivative operators, dy and d by dz. Okay, so it acts by itself on scalars. So the gradient of the pressure, I should be consistent here. The gradient of the pressure is a vector where the x component of the vector is the partial derivative of the pressure in the x direction, and then the y component is the partial derivative of the pressure in the y direction, and then the z component is the partial derivative of the pressure in the z direction, right? So this is actually a vector quantity that has a physical interpretation, this thing on the right. This is an operator. Okay, so by itself, this doesn't mean anything. It has to act on something. There's also the Laplacian, which is, not the plus sign there, which is another operator. It's the result of taking the dot product of these two operators, right? So it's the second derivative, second partial derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z. Still another operator, right? Waiting to act on something like the Laplacian of the pressure, for example. You can guess what it would be based on, you know, the relationship between the above two lines. Okay, this thing can also just be a dot product. You can like here in the Navier-Stokes equation, you see v dot the gradient operator, and this thing is still an operator because there's nothing on the right hand side. The gradient operator acts on something immediately to the right of it. All these operators do. Okay, so if there's nothing there where I just put those three red circles, then you know that it's still acting like an operator. So this thing is still, what it ends up being is u times d by dx plus v times d by dy plus w times d by dz. And this thing is still waiting to act on something. In this case, right here, which I'll underline in red, it's acting on the v component of the flow velocity. Okay, so hopefully that's a useful explanation of what I mean by these vector operators. And now let's actually use some of the symmetry. Use symmetry to simplify the equation. So first off, we know in the fully developed region, since the flow conditions are not changing in the direction along of the flow, that means that the partial derivative with respect to y is equal to 0. That operator is the same thing as multiplying by 0. Okay. Also in the fully developed region, in that same region, we know that u and w, the flow, the components of the flow in the x and z directions respectively, are both equal to 0. Right, and we kind of discussed that above. That's why we only focused on the y component of the overall set of Navier-Stokes equations. So if we were to look at this operator, v times gradient, or the dot product of v with the gradient, it ends up being equal to u times d by dx plus v times d by dy plus w times d by dz. Okay, so we just said that d by dy is equal to 0. And we know that w is equal to 0 and u is equal to 0. So this whole thing is equal to 0. Okay, so this middle term here, right here, is going to go to 0 because of this, these two symmetry arguments. Okay, and then we also, since the problem is 2D, what we mean by that is that we're assuming that everything's sort of infinite in and out of the page. That means that d by dz, that nothing is changing in the direction out of the page. So d by dz is equal to 0. So because of that, if we look at the Laplacian of v, where we have d squared v dx squared plus d squared v dy squared plus d squared v dz squared, this term goes to 0. Okay, and then we'll also assume steady state, which in effect is saying that the partial derivative with respect to time is also acting like a multiplication by 0. Okay, we should also note that the fully developed thing here leads to this going to 0 too. Okay, so what are we left with? Well, what we are left with in the end is the following differential equation, where we just have mu times the second derivative, and here we can switch to a total derivative because we've kind of gotten rid of all of the other independent variables involved. The second derivative of the y the y component of the flow velocity in the fully developed region times mu is equal to rho g. Okay, and then we'll assume that v at x equals 0, so right at the wall, is equal to the conveyor belt speed, v naught. V naught, the conveyor belt speed. This is often called a no-slip condition. And also, no shear. So that means that the no shear at the air interface. So what we mean by that is that mathematically what that means is that mu dv dx at x equals h is equal to 0. Okay, so that's true. But what that means is that there's basically the friction between the flow and the air is so small that the air is not going to cause any sort of change in the properties of v in the x direction. Okay, and so since we've specified these two conditions at these two locations, this results in a boundary value problem. Okay, and we also solve this. This is a second order non-homogeneous equation, but it's integrable. So we can literally just integrate this twice. You'll see that you'll end up with some sort of linear flow profile, subject to these conditions. Okay, so that's setting up that model. Excuse me. And then a couple more examples. So the first one that we'll talk about is just another sort of classic example, like a projectile. But here we'll talk about a football. So we're going to look at the trajectory of a football. Football trajectory. We're going to neglect the spin of the football and the lift force, and then we're going to track the coordinates of the centroid. Centroid meaning the center of mass of the football. Okay, so here's where we're going to end up with a coupled set of differential equations. So first off, we know that dx of the ball, the position of the ball in the x direction, dt, is, we can define that as ub, right? The velocity of the football in the x direction. Same with dy ball dt is equal to vb. And then from Newton's second law, we know that the mass of the ball times du b dt is equal to minus f cosine theta. Here, let me draw. I should have drawn the diagram first, but I will after writing these equations down. mb dv ball dt is equal to minus f sine of theta minus the weight of the ball. So okay, so let's draw the ball here. So we have the ball. Not my best work, but it'll do. And it's traveling at this velocity, which has two components. So x component ub and a y component vb, right? The theta that we're talking about here is this theta, which we can see is just equal to the arctangent of vb over ub, right? And then we have some diameter, cross-sectional diameter of the ball d, and of course the ball weight is acting down w. which is equal to the mass of the ball times g in the negative y hat direction. Okay. Now, what is the force? Okay, so the force, we're going to say that we know some coefficient of drag, and we'll multiply that by rho over 2, rho of air that is, times u ball squared plus v ball squared, sorry, the magnitude of the velocity squared, times pi d squared over 4. All that forms the cross-sectional area. Okay, so that's the force due to drag on the ball, and then we'll have the initial conditions, which are that x of the ball at 0 is equal to 0, and then y of the ball at 0 is roughly the height of the quarterback throwing the ball, so it's about 6 feet. We'll say that the speed, u ball squared plus v ball squared raised to the 1/2 at t equals t naught, or t equals 0, is equal to 55 miles per hour. And we'll say that this is launched at t equals 0 at about a 45-degree angle. Okay, so we have 4 coupled differential equations here. That could be, combined to form 2 differential equations. And they're all homogeneous, with the exception of the equation with the weight. And we have 2 linear equations and 2 nonlinear equations in this set of first order ODEs. Okay, so like I said, we have a set of 4 first order ODEs, but we could combine them and to form 2 second order ODEs, but we would still, because we had 2 second order ODEs, we would still need those 4 conditions. Okay, nice simple model for the trajectory of a football. And then for our last example, we will talk about unsteady conduction. Whoops. And this is more of a preview than a detailed discussion for this here. So we're going to talk about the heat equation. What I'm going to say here is that you're going to have a partial differential equation. So the heat equation is the partial derivative of the temperature with respect to time is equal to the Laplacian of T, which is expanded out d squared T dx squared plus d squared T dy squared plus the second derivative of T with respect to z. Okay, and this Fourier developed the heat equation actually the same year that Navier worked on viscous flow. So this is a portrait of Joseph Fourier, who has a whole host of amazing contributions. In fact, we will also go through Fourier series in this course and the Fourier transform later on. It's one of kind of the extra topics that we'll cover if we get to it at the end of the class. But you can see what the heat equation generally does here. So like I said, this is a bit of a preview, because we're actually going to solve these partial differential equations later on in the class. But what the heat equation does when the Laplacian operator appears at the same time as a partial derivative in time, what it does is it smears things out. Okay, so you can see that at t equals 0, you start with a very sharp profile of whatever the dependent variable is. In this case, it's just u. And you can see as time goes out, it kind of spreads out. And so part of what the intuition that I want you to take away from this course is I want you to be able to glance at a differential equation and say, oh, that has what's called a diffusion term, which is a term that has the Laplacian in it like that. And diffusion terms is the reason why it's called that is because it causes the concentrations of the dependent variable to spread out, to diffuse throughout space. Okay, so this is one of the ways that, at a glance you can look at a PDE and see. You could look at a PDE and you could look at it as a numerical solution. You could guess that one of the terms is leading to the type of physical phenomena that you're seeing, or like you might see that the numerical solution to a specific problem has this spreading out feature is really strong. It's spreading out quickly, or that's the dominant behavior. So you can tell that term in the differential equation is dominating over something else like an advection term, which is another type of term that shows material being transported through space. Okay, so the advection diffusion equation is a very, very common type of transport equation that we will encounter in this class. So yeah, just wanted to make that note there, show you guys a portrait of Fourier and give you a preview. In a 1D system, the equation simplifies to just the partial derivative of the temperature with respect to time is equal to the second derivative of t with respect to x. Right? This is like modeling something like a long, thin rod. You could think is something that's approximately one-dimensional. Okay. So typically, you'll specify t of x. So you'll specify the entire spatial profile of the temperature at t equals 0. Okay, and hold the temperature at some specified values at the boundaries. So, like, you have t at x equals 0 for all time is held at 100 degrees Celsius, and t at x equals L at all times is held at 50 degrees Celsius, right? And so in that way, this partial differential equation is a first order initial value problem in time, right? Because you're along the time axis, you specify everything at t equals 0, and then you allow it to evolve in time. And then it's a second order boundary value problem in space or in x. Okay, and that's where you see that those two values being specified at the boundaries. This might sound a little confusing right now, but as time goes on, we will make it more clear, and you'll become confident with this whole idea, with solving a partial differential equation and understanding what we mean by saying it's a first order initial value problem in time and a second order boundary value problem in x. We'll show you some plots and you'll see the way those solutions work. Okay, so normally, or not normally, but at this point is the time where we need to move on to Taylor series, and since it's such a big topic, and such a change in topic from the modeling basics, I'll go ahead and leave that for the next lecture. So you'll have that to look forward to. It's extremely fundamental to literally everything that we do for the rest of the course. So I'm gonna, try to spend some extra time on this and make sure that it's very clear, and I definitely these versions of the lectures are still not perfect. So we'll continue to try to improve them as time goes on. But when I taught this class, Taylor series were especially explaining the theoretical underpinnings and the basic ideas were among the biggest disconnection points for students before, and it's the most important foundation for everything that we do going forward. So we'll really try to hit that hard, and I encourage you to look at supplemental material to really understand these things. And I'll in the next lecture, in the description, I'll point you in the direction of some really nice videos, in particular by Grant Sanderson, that I think do a great job of illustrating the idea. Okay, so for now, thanks for listening, and I will see you next time. Take care.